Good morning, everybody. This is exciting because now, if you've been around for the past couple sessions, we talked all about how to use R, how to make pretty pictures with R, but now we're going to start talking about what we can actually do um, with R to actually analyze data and prove causation, which is hopefully what you all care about the most. When you do policy analysis, you want to convince people that the policies that you talk about and that you implement actually have an effect. So that's what we're going to be talking about today, is how to actually prove causation and legally talk about causation. And I say legally because you've probably all, in any stats class you've ever had, you've always heard like correlation is not causation. Don't talk about causation. If you look at a regression output, you can see all the cool coefficients and stuff, but you can't say anything about causation. That's like illegal. So what we want to do is move beyond that and actually start talking about causation. Um, and this is important because in the policy world, there's this increasing movement to actually care about causation and try to find evidence, a causal evidence for every policy. So, quick question for all of you: is it possible to measure evidence for policies and programs? Go ahead and in the chat say yes or no, and we'll see what you all think about that. Guessing it's overwhelmingly going to be one answer, but we can check just to make sure. You're all saying yes and hope so. Yes. So we all hope so too. That's what we're doing here. So the issue with this, though, is it is hard to prove causation. In the hard sciences, it's fairly easy to prove causation. You can say that water is two hydrogens and one oxygen, and you can put them together like two hydrogen molecules, one oxygen molecule, and it will turn into water. And you know that that's a causal relationship. You doing something creates water. People are dumb though and don't respond like molecules, which are even dumber because they don't like think. People do think, and so it's really, really hard to prove actual causation in the social sciences. There are lots of efforts to do this. There's a whole world of trying to prove evidence-based policy. So back in the 1950s, the whole reason we have private insurance connected to private employers in the United States is because the Rand Corporation in the 1950s led a study on health insurance. It was a randomized controlled trial to see what was the cheapest, most cost-effective way of delivering healthcare to kind of the whole country. And they discovered that if you have private insurance, there's less use of healthcare, and people don't go to the doctor as often. And so policymakers back then said, "That's awesome, let's do it." And so that's why we have it, which has not been great for like access to healthcare. But it was based on kind of a randomized control trial that happened years and years ago. With the expansion of Medicaid following the Affordable Care Act, states have been jumping on board this whole finding policy thing, or finding evidence for policy thing. And so in Oregon, they had extra money for expanding Medicaid. And so they had a lottery system where they offered some people free Medicaid, and other people weren't able to get it. And so they've been able to measure the causal effect of having Medicaid and having access to medical care. And they found that in general, people who have gotten that extra Medicaid have been healthier, which again is not super surprising, but there's evidence for it. Lots of federal agencies have been doing this. Housing and Urban Development, they have a long-running program called Moving to Opportunity, where they had a randomized lottery system for giving people vouchers for moving from poor neighborhoods to rich neighborhoods to see what the long-term effects of moving to a different geography was. And they found that it has had some effects at improving poverty, especially in the second generation. So kids who get to move to better neighborhoods do better. And then the Tennessee Star experiment was this kind of small scale randomized control trial to see if class sizes mattered in elementary schools. And they found that smaller classes generally lead to better test scores. So we have all of this cool evidence of like social programs based on randomized controlled trials, based on other ways of gathering evidence. And so it's an exciting way of thinking about policy instead of just saying, I think this might work, let's try it, which is good. This is how we all do stuff. That's the only way to get things started. But then to think about it more systematically in a way to gather evidence so you can prove causation. That's where it gets more exciting. There's actually a whole industry around this now. There's the Jameel Poverty Action Lab at MIT, or JPAL. They run all sorts of experiments in the developing world trying to fix poverty. Their founders just got the Nobel Prize in economics last year for all of their randomized control trials, and so they do cool stuff. There's also this organization called the Campbell Collaboration. If you go to Google and search for that, it's just a huge library of policy evidence. If you want any sort of trial or any sort of published evidence for any sort of policy you're interested in, they have a search engine there. You can search for whatever evidence you want based on either trials or other fancy ways of finding causal inference. Okay, so with that, let's ask another question. Should we have evidence for every policy or program? Should every policy we implement be backed by some randomized control trial? Go ahead in the chat, answer that question. What do you think? No. Why no? Somebody justify your answer. We care about causation. We care about all this analysis. So why don't we need evidence for everything? Not feasible, unethical. Yeah, so not everything can be measured. New studies have no evidence, especially for new phenomena. It's really hard to do any randomized control trials for policy interventions for like COVID-19 right now because it's only been around for a few months. And so it's hard. Unethical. There's just an experiment that was published, or a preprint came out that showed that there's this randomized control trial in Kenya where people were randomly assigned to have their utilities shut off, which is wildly unethical. And so people went months without like water and electricity in the urban poor areas of Kenya, just for the sake of evidence. Which, like, don't do that. That's bad. I don't know how they passed IRB with that. Like, don't do that. So yeah, the answer I argue here is no, because lots of kind of deciding to do policy is based on intuition or just based on other things that aren't trials. So there's this idea here, like if you don't smoke, you already believe in causal inference without randomized control trials. There's never been an RCT or randomized control trial for smoking. The only way that would work is if you found a group of like 800 people and assigned 400 of them to smoke for 40 years and assigned 400 of them to not smoke for 40 years, and then see what happens at the end of the 40 years. Nobody's done that because that's unethical. But we have other statsy ways of finding that causation without having to run an unethical trial. So there's no reason to do that. Same thing here with driving laws. Or the age of buying alcohol and connecting that to driving. There's been no randomized control trial over what the legal age should be for drinking. Instead, states have kind of played around with it, and they've tried different experiments. They've not systematic experiments. It's just like one state decides that we'll have the drinking age be 19, or one will do it at 18, one will do it at 21, and then you can see what the changes in the deaths from motor vehicle accidents are. You can do other ways of trying to find causal inference without running an actual randomized control trial, because again, in this situation, it's going to be wildly unethical. So with this, program evaluation is essentially a way of trying to find the effectiveness of a program and prove its causation and prove the causal effect that it has. Kind of the easy way of thinking about it here is this right here. This shows a hypothetical program that's trying to boost student grades. It shows here that you have kind of before the program, the grades are low. During the program, something happens. And then after the program, if you're in the program, your grades are higher. And if you're not in the program, your grades are a little bit lower. That right there, that up and down vertical effect there, that's the thing we care about. So in any program, you want to be able to find that effect and prove that there's causation. And if you can prove that convincingly using statistics and using kind of a good argument of your causal philosophy, then you can prove that your policy is effective, even if it's not a randomized controlled trial. So here, this is from an evaluation that I ran a few years ago for a school district in Utah. I'm looking at a program that was trying to intervene in truancy and getting students to come to class more often. And so you can see the students that had this intervention The program here happened at week 0. And then this is what actually happened after the program. You can see the average number of absences started dropping off. And using fancy stats tools, we estimated that this would have been what would have happened had the program not occurred. And so the difference here between this predicted truancy, the predicted absences and the actual absences, that is the effect of the program. And so we were able to convince state funders to give this program more money because it had a causal impact. So this does have like real life consequences. So the issue here, though, is at the beginning, I mentioned that many of you are probably scared of causation because of how your stats classes have taught you about causation and correlation. And so what I want to introduce really quick is this idea of Godwin's law. Which is actually an internet thing where, according to Godwin's law, the probability that somebody in some discussion on Facebook or Twitter or somewhere, especially if it's a political discussion, the probability that somebody's going to mention Hitler always happens as the conversation goes by. And this is the idea of Godwin's law here. And so as an online discussion grows longer, the probability of somebody mentioning Hitler approaches 1. And you've seen this in your everyday life. With neighbors and with family, somebody will always bring up the Holocaust or Nazis if you're trying to talk about like American politics. And when that happens, it kind of shuts down the conversation because nobody's worse than that. And so you can't really talk about that anymore. There is a version of Godwin's law, I argue, for statistics. And it is this phrase here, that correlation does not imply causation. And you'll see this all the time. You've probably even said this all the time where somebody presents some cool argument or you see a new study online and one of the first comments, or maybe in your head, you think, oh, that's just correlation. No, that's not causation. And the issue there is as soon as you say that, it kind of ends the conversation. And so often, if you do have a causal relationship, there is correlation too. And so it's kind of a useless phrase. And I would argue don't always say that because there can be causation. Even if you see correlation, there's probably a causal story somewhere buried in there too. So the difference between the two, though, is a little bit tricky. So with correlation, how do you figure out correlation? It's just math. There's a formula that you can use. It's built into Excel. It's built into Stata, built into R. And so it's just math and stats, and you can figure out how correlated two things are. How do you figure out causation, though? There's no causation function in Excel or R or Stata. You can't just say, like, make this causal. It's not a question of math. Instead, it's a question of philosophy. And it's a question of trying to figure out links between different variables that you have. So with that, how do you know if X, something out in the world, some policy, causes Y, some outcome? Go ahead and in the chat, tell me what you think. How do you know if something causes something else? We're humans. We're really good at this. Some statisticians have argued that this is what makes us human, is that we understand causation while like deer and raccoons don't. So you're all good at this. What does it mean if X causes Y? So if we see lots of cases of X leading to Y, so if we see a history of X causing Y, that's one example. What else? Okay, so experimentation, you only change X. You can predict the outcome of Y based on what you know about X. So controlling all other factors and only changing X. Okay, those are all good. X happens before Y, and we can rule out all possible causes. So that is good. And we need all of those pieces of that definition, because if we just say lots of cases of X lead to Y, then that actually leads us to this situation where lighting fireworks does cause noise. Yes, that's a causal relationship. Rooster crows are always followed by the sunrise. Therefore, roosters cause the sun to rise. We can see that happens like every day on farms. We have lots of X's there, and it always leads to the same outcome. But in this situation, that's not a causal relationship. There's something else happening, like the sun does its own thing. So roosters don't cause the sun to rise. So in that situation, what I would argue, kind of the simplest way to think about causation for today, is X causes Y if we do something and change X without changing anything else, and Y changes. And so one of you said we can control other factors and only change X. That's this example here. So if we want to know if the rooster is causing the sunrise, then we hide the rooster one night and see if the sun still comes up. And if it does, then it's not the rooster, it's something else. So another way of thinking about this is that Y listens to X. So it responds to it. So X isn't going to be the only thing that causes Y. There's going to be a billion things that cause poverty, they cause health, they cause kind of these big social phenomena that we care about. But there are lots of things that affect that. So like this here, this light switch example, you can have a light switch turning on or a light bulb turning on. That's going to be the Y. You can have X be the actual switch. It might turn on if the bulb's not burned out or if the wiring is good, or if it's not already on. But there are other things that can influence whether or not that light bulb is on. If there's electricity going through the house, there's a whole bunch of different moving parts there. But there is a clear causal relationship between the switch going on and the light bulb going on. Okay, so beyond the whole listening idea, this is kind of another way of thinking about it. Causation is correlation plus time order plus all other factors are ruled out. So the rooster, there is correlation. Time order is backwards. The rooster's making its noise at the sun because it's coming up, not causing it to come up. And all other factors ruled out, like there's space, there's orbits. It's not just the rooster. So there's no causal story there. So how do you know if you have a causal story and it is right? That's really hard. And there's no good way of knowing it unless you have a philosophical model of the causal story that you care about. And that's what this workshop is for. It's talking about how to create a philosophical model for a causal story and then test that philosophical model. And once you can do that, then you can tell a convincing story about causation. And that's what we care about. So our plan for today is we're going to spend the first little bit talking about this idea of directed acyclic graphs, or DAGs, and this new thing called the causal revolution that's been taking over social science, at least over the past 5 or 10 years. It's this idea that started in computer science 20 or 30 years ago, and it's kind of taken off because it's a really easy way of thinking about causation, a very systematic way of thinking about causation, and it actually informs your analysis once you can understand these graphs and how everything's connected. So we'll spend some time there. Then we'll briefly show how to prove causation using randomized control trials. And I have a whole bunch of R code that we'll walk through so you can see how you can analyze this stuff in real life. Then we'll talk about this fun, controversial thing here. You can actually prove causation using just regression and not even fancy, like scary regression with like instrumental variables or anything. If you have a good causal diagram and you believe that it is complete and that it shows all of the causal relationships, you can actually block all of the different relationships that you don't need, and you can isolate the one causal relationship you care about. And you can do that potentially with just regular regression analysis. And so we'll show an example of that. And then near the end, we'll go over two kind of standard approaches that you see in policy analysis. These come from econometrics, which is kind of statistics for economics. These are different ways of also proving causation using observational data. Difference and difference analysis, and then regression discontinuity analysis. And so I have some R code that we can walk through there so you can see different examples of how this works in real life. So that's the plan. It should be fun and exciting. We'll be doing it in RStudio. If you go to this URL here, andhs.co/GPL causation, it will open up an RStudio.cloud instance where you can follow along with the code. So go ahead and go there. I'll put it in the chat too. Okay, so if you click on that link in the chat, it should take you to RStudio Cloud. If you're not logged in, it'll have you log in. So go ahead and go there, and we will start talking about causal diagrams. All right, so let's talk about the causal revolution. So before we do this, we need to talk about two different types of data that you'll come across in the world. The first is experimental data, This is data that comes out of like a randomized control trial. It's when you have control over who gets the treatment and who does not, who gets access to a program and who does not. So that's fun because people love this kind of stuff because you can prove causation. That's the whole reason you run an experiment is you can say, does this program have a causal effect? Does it boost grades? Does it boost health? Does it boost incomes? There's also observational data, which is data that is collected after the fact, after you have a program that's been implemented. You don't have control over which units get the treatment. You don't have control over who gets to sign up for the program, over who stays with the program. It's kind of after the program has been rolled out, then you get to look at it and see if it had an effect. So my question for all of you is, which of these kinds lets you prove causation? Go ahead and in the chat, tell me which you think proves causation. You're all optimists. It can be both. And this is true. This is good because like 20 years ago, you would have all just said experimental only. We can't use any observational data ever. And so don't even try. But we can prove causation using observational data. It is entirely possible. And so can you prove causation with observational data? Yes. But why is it so controversial to use observational data? Why is it that 20 years ago people were saying, no, only experiments? Why is there some hesitation? Even some of you say here, the probability is higher for experimental data, or experimental data is better, but observational can maybe work. So why is that? Why are we all afraid of observational data? Okay, so bias, like selection bias, if you're looking at data that's observational, people who need the program are going to join the program and people who don't need it won't. And so that means the people who need it are going to be helped by it. And so it's going to work for them. There are confounding factors. Yeah. And we've always been taught that the gold standard is randomized control trials. And sure, we'll talk about that later. That's not actually super accurate anymore. Okay. So we can do this with observational data. And that's where this causal revolution comes from here. So this guy here, he's a computer scientist from Israel. His name is Udaya Pearl. He's been working on this causal inference stuff for decades. This book here, the Book of Why, is kind of the most accessible to the public version of his stuff. I recommend it. It's like super accessible. It's a fun book. He spends like a third of it yelling at scientists for not believing in him. And he's just like, tells grumpy old man stories, and it's great. But what is at the core of this causal revolution idea is that he argues that you can prove causation using observational data without experiments, and there are ways of doing that. And the way you do this is using these things called causal diagrams, or directed acyclic graphs, or DAGs. So directed means that these different nodes here have arrows that point. So that's the directed side. Acyclic means that you can't cycle back to one of the nodes. So I can't go from point Z here to X to Y and back to Z. You can't have two directional arrows. Everything's just kind of in one direction. And then graph is a graph. So we call these DAGs. And what these are is it's a graphical model of your philosophical model. It basically maps the philosophy of your causal story into a picture. And the most exciting part about it is it lets you do this fancy math stuff called do calculus that lets you isolate causal relationships here. So if you look at this picture, this shows that X causes Y, sure, but it also shows that something else, Z, causes both X and Y. And so that is confounding that relationship there between X and Y. And so if we can do something to block Z, to make it so Z does not influence X and Y, then all we're left with is the causal relationship between X and Y. And then we can prove causation. Whatever that relationship is, if it's a regression coefficient or something, that's going to be the causal effect of this program X on the outcome Y. But we know what we need to control for. We know what we need to adjust for because of this graph. We can see that Z is confounding both of those things. And so using this graph, it essentially tells us how to analyze the data, this observational data, so that we can tell a causal story. Okay, so we're going to do an example of building one of these directed acyclic graphs, or DAGs. So we'll use this question here. What is the causal effect of an additional year of education, university education, on earnings? This is a very typical econometric question. There are like a billion papers about this. So we'll just do a simplified version of this here and draw a DAG for it. So the process that you go through when you're drawing these DAGs is first you list all of the variables that you think might be important in influencing both the program, like education, and the outcome, like earnings. Then you simplify those variables down so it doesn't get too unwieldy. Then you connect the arrows. If you say like, if one of these things causes education, then draw an arrow point, like connecting the thing that you care about to education. And then you can use logic and math and other fancy do calculus type stuff to figure out which nodes, which variables you need to actually control for and what you need to care about. So here's an example here. So education is going to be our treatment, and then earnings is going to be our outcome. Here's a whole bunch of different things that influence either one or the other or both. So where you're born, how good you are at going to school and taking tests, the year of your birth, socioeconomic status, laws that require you to go to school, those cause education. Having good job connections, that helps find a job and helps improve your earnings. There could be a ton of other things in here. This is just kind of what I thought of just off the top of my head here. Then we can simplify these things. With ability and demographics and socioeconomic status, we can just kind of collapse those all into something that we'll just call background. Again, these don't necessarily have to be measurable. These all could be kind of columns in a data set, but not necessarily like ability. How are you going to measure that? Good luck. Background, how are you going to measure that? Even if you collapse demographics and socioeconomic status and all of that stuff. This is all just kind of at the philosophical level. You don't need to worry about connecting these to actual measured things yet. So what we're left with is location, year of birth, compulsory schooling laws, job connections, and background. Then we can start drawing arrows. So here we say that education causes earnings. So we can see there's an arrow between these two nodes. So each of these dots here is called a node in a graph. So we're just saying education causes earnings. The arrow means it has a causal relationship. It's not associated, it's actual causation. So that's what we're trying to measure here. Is we say education causes earnings. But all of these other things cause education. So your background, your location, the year you're born, a required schooling, that all causes education. And so they also point into that education node like that. Then we can connect them to earnings. We can say the year that you're born, your location, your background all cause your earnings. If you're born in a year where like 18 years later, there's an awful recession, that's going to be bad for your earnings. Job connections causes earnings. Job connections don't really cause education. That doesn't make you go to school more. That's kind of independent of that. Required schooling doesn't cause earnings directly. And so you can kind of see the philosophy of all of these relationships already just kind of laid out in the graph here. So you can see that required schooling doesn't directly cause earnings. There's no connection here. So any arrow you don't include is making a statement saying there's no relationship between these things. Then we can also say that education causes job connections. That's a typo there, not job earnings. So going to university gets you networking, gets you friends, and then gets you connections for future jobs. And so there is kind of that causal relationship there, which then causes earnings. Okay, so what we're left with is this graph here. We'll add one more node here. Something causes you to be born in some location and to have a specific background, to have your parents have some sort of income, different socioeconomic status factors. There's something unmeasurable that causes both of those. So we can include unmeasured things in there. And we'll just call this U1. We could imagine U2, U3, other unobserved things out in this graph. So this is our final causal graph for earnings, for the relationship between education and earnings. And the cool thing about this is once you have this mapped out, if you then go present to somebody and say, here's what I think the relationship between education and earnings is, and here's how I estimated it, people can argue and critique your model based on this picture. They can say, I think there should be an arrow from this node to here, or I think you should include one of these nodes. Instead of them just saying correlation isn't causation, ha, got you. This provides you kind of a smart way of talking about the causal relationships. especially when we get to this idea of closing doors and isolating arrows. As long as like you have this common foundation here where people can critique you, people can argue about this, but then you can still analyze the data and make good causal inferences based on your data here. So that's kind of a simplified DAG that we just drew here. So what I want to do is for the next few minutes, I want you all to draw a DAG. But before I show you the scenario for the DAG, let me show you the easiest way to do it. You can either do it on paper, that's great, or there's a website called daggitty.net with 2 T's. So Dagitty. Let me stick it in the chat here. This lets you draw DAGs. So if you click on this first link here, this launch, it will launch Daggitty in your browser. You can technically download it. I've never done that. And so here is this empty canvas here. It gives you kind of this M-shaped DAG. What I like to do is go to model and then new model, and then that just gives you an empty canvas. So to make a node, you just click somewhere and we can name it something. We'll name this X. And now we have an X node. To make another node, you just click somewhere and we'll name that Y. And then to make another node, we'll just make one called Z. So we have all these nodes just kind of floating around. If we want to connect them, then you click on one of them. So we want to say Z causes X. And we're going to click on Z, and then we're going to click on X, and it will draw an arrow. And then we can say Z causes Y, and we can say X causes Y. So now we have our little DAG here. You can move the other nodes around. Importantly, you can set some of these to be the outcome and the treatment. So you can say X is our treatment. Daggitty calls it exposure. So if I select X and then click on the exposure checkbox up in the top corner, now that is the exposure. So that's the treatment. And then Y is going to be the outcome. So we'll select Y and say outcome. And you'll notice it highlighted Z and in red. It said that Z is messing up that relationship. And we'll talk more about that in a minute. So that's how Daggitty works. So what I want you to do is for the next few minutes, 5 minutes, I want you to try to tell a causal story here. Does a longer night's sleep extend your lifespan? So the treatment is more sleep. The outcome is life expectancy. So what I want you to do is go through these steps. List all the variables that you think influence either amount of sleep or lifespan or both. Simplify that list down and then start connecting arrows. And use Daggitty or use pen and paper and take 5 minutes to do that, and we'll share what you've found after 5 minutes. 1, 2, 3, go. And ask any questions you have in the chat while we work on this. And we'll see what you come up with. All right, the time is up. So who's going to volunteer? I will stop sharing my screen and we'll see what fancy DAG 2 of you came up with.
We got the outcome over here, more sleep. The outcome is longer life. And primary input that we were interested in, the exposure, is more sleep. And I just got a bunch of things that I think could be related to either of those: health, age, genetics, birth, family. Well, I'm not sure what else to say about it.
Cool. No, that's great. And the fun thing about this is if you're presenting this at a seminar or something, people could start arguing about your DAG, and they could say maybe your job causes your health too, and you're missing an arrow there. So you can say, sure, there's an arrow there, and then you can see if that messes up your causal effect. So like it gives a good foundation for talking about this. Or for finding more research. You could say, is there a relationship between job and health? Maybe, maybe not. So that looks great. You also notice how age and health and genetics are red, but the others are green. That's because Daggitty magically figures out the connections between these and what might be confounding. So in this situation, genetics and age and health are all confounding factors. And so based on this, it says that we should actually control for those and take those into account. And once we do, we should be able to tell a causal story, even if like we don't need to worry about health or wealth or job or family. because according to the DAG here, they're not connected to longer life. There's no association there. And so it kind of explains what you need to analyze in order to tell the causal story. So that looks great. Cool. Thank you. Anybody else? We need one more volunteer to show their graph. And then keep that graph up because we're going to come back to it in a bit. So here we have a ton of things causing sleep. So mattress comfort and safety. But then none of those things are connected to lifespan. And so again, if you were presenting this in like a seminar, then people could start saying maybe some of those things do influence health or lifespan as well. And then once you start connecting things to both the treatment and the outcome, that's where you get all sorts of insight into what you should actually analyze and what you should actually control for. So looks great. Good job, everybody. You made your first DAGs, and DAGs are great. Okay, so let's switch back to me, and we'll talk more about how to analyze these DAGs here. So if we go back to here, what we care about the most in this situation is this relationship between education and earnings. This arrow right there is our causal effect. That's what we need some number for. We want to be able to say 1 year of education leads to some amount of earnings. But all of these arrows also pass other associations on. So required schooling causes you to get more education. Having job connections causes you to get more earnings. And so we want to isolate just that one arrow. So how do we do that? What about all those other nodes? So what we care about is something called causal identification. And so this idea of identification just means that that arrow is isolated. And if we can isolate that arrow, then we have a causal effect. So in a DAG, the logic behind these DAGs tells you how to isolate that effect. So each of those arrows transmits some sorts of association, and you can actually redirect those associations by blocking different paths. And so if there's this old iPhone game from like 10 years ago called Where's My Water, where you have to direct this water through, like you have to dig a tunnel with your finger and you have to direct water to different pipes and you can control where the water is going. That's essentially what you're doing with these DAGs. You're saying there's some causal effect, there's some association that goes from one of these nodes to another node. You want to block that off so that all you're left with is the causal association between your treatment and your outcome. And if you can block all the other paths, then you're left with an identified causal effect, and then you can tell a causal story. And so you redirect things by doing something called adjusting or conditioning. So that's what we'll be talking about here. In general, there are 3 types of associations or links between nodes here. There's confounding, which we've kind of talked about already. It's this idea of having a common cause. So Z causes X and Z causes Y, and the X also causes Y. And so Z is messing up that relationship. It's confounding it. And so we'll talk about this in a minute. You can also have a causal story where X causes Z, Z causes Y. So this is kind of the job connection story, where education causes job connections and then job connections causes earnings. But also education causes earnings by itself. And so that's kind of the mediation here. The confounding from the example we've been looking at is like year. The year you're born causes you to get more education or less, and it also causes you to have higher earnings or lower earnings. So it does both. But then there's also this X to Y relationship that we care about. And then finally, we have this idea of collision, where X causes Z and Y causes Z, and then X causes Y here. And both of those arrows are pointing away. And if you control for Z or consider Z, it will actually mess up the relationship between X and Y and it will distort it. And so you don't want to control for Z in that situation. And why this is helpful is if you've ever taken a stats class where you learned about multiple regression and you had to build a regression model, you have to choose what variables to include in your model. And typically when we teach this, we just say, throw in whatever you think is likely. And so you just throw in a whole bunch of different independent variables and then run the regression and then throw some more in and run the regression and see what the effects are. And that's like the fun way of teaching stats. I used to teach stats that way too. It's neat, but it's wrong because if you care about causation, Sometimes controlling for things, like if you control for a collider, it's going to mess up your effect. If you control for a mediator, it's also going to mess up your effect. You do want to control for these confounders, but you don't want to control for these things. But if you're just throwing everything in the kitchen sink model, it's going to mess up your results. And so caring about these associations is important because we want to get the most isolated, most estimated, most accurate causal effect out of our models. So we'll talk about each of these three things here and what we can do using DAGs to isolate that X and Y relationship. So confounding here is this example where X causes Y, but Z also causes both of them. And so Z is confounding that relationship. So another way of talking about this using DAG language is that Z is a backdoor to the X and Y relationship here. And the way you can figure that out is if you write down all of the paths between X and Y. So you can go directly from X to Y. You can also go from Z to X to Y, or you can't go to Z to Y to X. So you can go Z, X, Y. So that's another path that you can go from X to Y using some sort of pathway there. The reason it's a backdoor is if you look right here, there's an arrow pointing backwards into X. So anytime you have some variable pointing back into your treatment, that's going to be a backdoor effect. And we don't want that. Okay, in official DAG language, this is called deconnection. So X and Y are deconnected because Z is messing it up. You don't need to worry about that so much, but if you come across this idea of deconnection or deseparation out in the world, that's what it's talking about. It just means there's a backdoor or the backdoor is not closed. Okay, so here's an example of a confounding backdoor. Let's say we think that there's a causal relationship between campaign money and win margin in an election. So the more money you raise, the higher the win margin is going to be. So that's our causal story. Campaign money causes a win margin. And but it's also confounded by this idea of candidate quality. So the higher quality you are as a candidate, the more money you're going to raise and the more you're going to win. So that is the confounding relationship there. So what we can do is actually write down all the pathways between campaign money and win margin. We have money leading to the win margin, but we also have quality being a backdoor to money there. And so quality is a backdoor. So we need to do something to fix that. So the way we fix that is we adjust for Z or control for Z. So that will close that backdoor and stop passing associations between Z and X and Z and Y. So in this campaign example here, what we want to do is find the part of campaign money that is explained just by quality. So how much of campaign money happens because of the quality of the candidate. Then we want to find part of the win margin that is explained by candidate quality. And if we erase that from both of those, from X and Y, then all we're left with is the part of win margin that is explained by campaign money, and that's our causal effect. And while that sounds kind of tricky, finding the residual part of campaign money and win margin, that's what regression is. When you control for something, you're taking the effect of that thing that you're controlling for out of the other variables. And so that's essentially what regression is here. Okay, so closing doors is really just controlling for these things or adjusting for these things. And what that lets us do is compare candidates as if they had the same quality. So it gets rid of the quality aspect and we're just looking at money and margin. And that lets us tell the causal effect. So that's how we adjust here. So different ways of doing that. Oh, the math got messed up here. Math is super messed up here. On your screens, when you follow along later, you'll see the actual math here. But so there are different ways of adjusting. You can just include the term in a regression model. So here you can see campaign money is there, candidate quality is there. So if you include both of those things in a regression model, then you're gonna adjust for quality. You can also do things like matching or stratifying. Stratifying would mean you find all of the high quality candidates and just do a regression on them. and then you do all of the low quality candidates and just do regression on them. And that lets you get rid of the quality aspect, and then it lets you isolate just that one causal effect. And then finally, there's this idea of inverse probability weighting that also lets you kind of find or adjust for quality or adjust for all the different confounders. Okay, so once you control for this confounder here, then X and Y are what are called de-separated or isolated. And so then that relationship there is identified. And you can arguably legally talk about causation now. Okay, so in here, here's a more complicated example. What your goal with situations like this is to isolate the relationship between education and earnings. So you want to figure out what things you need to control for to make sure that relationship is isolated. You don't have to control for everything, and you don't want to control for everything. Back when you learned about regression, you would just throw everything in here. You'd throw required schooling or job connections or other things in there. But in this situation, all you really care about are the things that are messing up the path between education and earnings. Required schooling doesn't mess up that path. It causes education, sure, but then education and earnings, like required schooling is not anywhere along that path, so we don't care about it. What we care about are the things that confound. So year causes education and earnings. Location causes both. Background causes both. So we need to adjust for all three of those things. Okay, we can actually write down all of the paths. This is something that Daggity does for you, which is nice because this gets really tedious. And so if you write down all the paths between education and earnings, here they are. And you notice these purple ones have backdoors. So background is a backdoor to education. Location is a backdoor. Year is a backdoor. So if you can control for just those three things, year, location, and background, according to this DAG, that is enough to isolate that relationship. You don't need to control for job connections. You don't need to control for required schooling. Unobserved stuff, we can't observe it, but because of how we've drawn the DAG here, we don't need to control for it. Because all of the stuff, all of the associations that come from this unobserved stuff gets blocked by location and background, and it doesn't make its way down to education and earnings. If we can close these backdoors here, everything behind those nodes gets blocked off naturally by itself, which is really cool. So we want to adjust for year, location, background, and that is enough to isolate the relationship. And then we can start talking about a causal effect, which is really cool. So the computer will let you do this. So if we look at Daggity really quick, if you've noticed, with some of you here, we'll add another couple nodes here just for fun. So if you look at my screen here, it says that Z is red, and then we'll just have Q cause Y and R cause X. So according to this, if you look up in the top right corner of Daggity, it will actually tell you what you need to control for. It says here that the minimal sufficient adjustment set for estimating effect of X on Y is Z. So right there, it's saying control for Z and you should be good. So to control for something in Daggity or adjust for something, you can select the node and then click on adjusted. And once you do that, notice how there's no longer any red. And now that relationship between X and Y is isolated. Even though we didn't control for R, we didn't control for Q, we didn't control for anything else, all we had to do is take care of that one confounder, and that was enough to isolate that relationship, which is really cool. And that's theoretically all you have to do as long as the DAG is complete. DAGs can get super complicated. Like this is a very simple one. If you look at the examples here in Daggity, one of these gets wild. Is it this one? Yeah, there's one. That's crazy. You can look at some other examples here. This is what DAGs look like in real life. Woo, that's a fun one. So this is saying tooth loss leads to mortality. But look at all these confounding related factors, and you need, but even though it looks really complicated, it says right here, if you want to isolate that relationship between tooth loss and mortality, control for those things. And that's what you need to do. And as long as you control for those things, then you should be able to tell a causal story about tooth loss and mortality, which is really neat. So that's how these DAGs work here. And Daggity is really nice because it handles it for you. Okay. Also, how do you know if it's right? So if you look right here in this picture, this is the education and earnings story that we've been talking about. If you look at the right side of Daggety, it has this whole list of what are called testable implications. And it has this upside down T thing. What that upside down T thing means is independence. So what this means is if we come back to oh, we lost our model. Let's make a super simple model, X and Y and Z. Z causes that, Z causes that, X causes Y. That is the exposure, that is the outcome. Okay, so what this means is if we control for Z, let's add one more. There it is. So we'll just add one more thing here. So if you look at the testable implications, what this means, Z is independent of Q. So that means there should be no relationship between Z and Q. According to this, there's no arrow between them. Z doesn't cause Q, Q doesn't cause Z. So if this is right, and we have a data set that has a column for Z and a column for Q, if we see if we check the correlation between the two and it's 0, then that means that's right. Like there's no arrow between them. And so that the DAG tells us that there should be no relationship between those. It also says Y is independent of Q for all, and then this line right here means given X and Z. So for any rows that have the same number for X and Z, whatever that is, if it's income or age or whatever, if you compare everybody that has the same income and age, there should be no relationship between Y and Q. And if there is, then that means your DAG is probably wrong. If there isn't, then that part of the DAG is right. And so you can actually statistically test each of these implications here to see if it is right in your existing data. And if it's not, then go back and fix it. If it is, then you got the DAG right, and you can tell a really convincing causal story. Okay. So in your sleep example that you did, you should have a big list of conditional independencies. And so you can go through, you don't need to worry about it right now, but you can look at it and say, is this thing really independent of that thing? And you can test those implications statistically if you had actual data for it. Okay, so that is how these DAGs work. Okay, the last few relationships that we care about. So we talked about confounding. Then we have this idea of causation, where X causes Y, X causes Z, which also causes Y. And so the question here is, do you need to adjust for Z? Should you control for Z? Should you include Z in your regression model? So with the education and earnings example, this is job connections. Should you control for job connections? And the answer is no. Even though it's not going to confound the relationship, it creates something called overcontrolling. What we care about is the overall total relationship between earnings or education and earnings. If we control for Z, what we're going to do is take from that total, the total effect, saying all of education causes some sort of earnings. If we control for Z, we're going to take out the part of education that's explained by earnings. We're just going to take out that tiny bit, which we don't want. We want the total effect of education. So we don't want to control for Z because that's going to reduce that total effect that we care about. And so you don't necessarily want to control for it. That's over controlling then. So back to here, should you control for job connections? No, because we care about education to earnings, the whole effect. If you control for job connections, that takes away some of that total effect. Okay, the last example here is this idea of collision, where X causes Y, we care about that, but also X causes Z and Y causes Z. So should you control for Z? Should you have this variable be in your model? The answer is no, because it will distort the effect even worse than controlling for a mediator. So here's an example here. Let's say you're interested in whether or not programming skills reduces social skills. So like these hardcore programmers are really big introverts or something like that. And so what you do is you conduct a survey in a tech company, because that's where lots of people with high programming skills are. And you try to see if there is a relationship between X and Y. And you find that it's negative. Having higher programming skills leads to worse social skills. Is that a real effect? And the answer is no, because you have a collider here. Another way of talking about colliders is selection bias. If you notice, having programming skills makes you get hired by a tech company. Having some level of social skills also makes you get hired by a tech company. So if you are conducting a survey only in a tech company, that's the same as adjusting for hired by tech company. And now you're limiting everything to just people in that tech company. And that's going to mess up your results. That's not for the whole general population. That is something called selection bias or adjusting for a collider. And so as a result, it messed up the relationship between X and Y here. Most often you'll see this collider idea when you're talking about selection bias. So here's another example here. If you look at this graph, this shows the height of basketball players and the number of points per game that they score. And if you notice, there's no relationship between height and points per game. So that means like anybody can play basketball. There's no relationship. You can be super short and still score lots of points. The issue here, though, is that's not entirely true. There's a collider here. This is for NBA players. So height is unrelated to basketball skill only for people in the NBA. So if you look at the DAG, though, height causes points to be scored, but also height makes you be in the NBA if you're super tall, and being really good at scoring points makes you be in the NBA. And so if you control for being in the NBA or adjust for that, or only look at people in the NBA, this relationship X to Y is going to be wrong. And so you don't want to do that. Like you are not going to tell a plausible story between X and Y because you're adjusting for that collider there and it's messing up the relationship. Okay, so these are the three types of relationships: confounding, causation, and collision. Daggity is really good at identifying these for you. When there's a collider, it will make it a different shade of pink, and so you'll be able to see that there's a collider there, and you can avoid it and not adjust for it. You can see the confounders, and it'll tell you what you need to adjust for to isolate this X and Y relationship. And so that is daggity. So next up, we're going to start analyzing some actual data or some simulated data using this idea of DAGs. We're going to first start with randomized controlled trials just because that's kind of the gold standard. And I'll show you how you can do that with R. And then we'll move into analyzing observational data and closing backdoors using this idea of DAGs. So let's go ahead and take a 5-minute break. And if you have any questions, put them in the chat and I'll answer the questions when we get back. So I will see you all back here in 5 minutes. Okay, so while everybody's coming back, we've got some good questions here. So how does Daggity know what connections to make? And can the assumptions be changed? So Daggity is not really doing anything magical. You can do all of this finding adjustment set stuff using like without Daggity. You can just make a list of all of the different pathways, figure out what things are backdoors, and then those are your confounders. Daggity just simplifies it for you. The way it knows what connections to make is like you tell it. So right now, like Z right here, by you saying I think Z causes X and I think Z causes Y, that is how it knows. You told it that. The fact that it's a confounder is because of the logic of DAGs. Like you're saying that associations can pass from X to Y, but can also pass from Z to X to Y. And so that makes Z a backdoor. That arrow is your fault. You chose that arrow. If somebody says, I don't think that's plausible, I think X causes Z, then sure, then you can fix that. And then according to the logic of these DAGs here, that's no longer a confounder. That's now a mediator because it's saying that X causes Z, which then causes Y. And then X also causes Y. And so you don't want to control for Z if you care about the X to Y relationship there. So it's really just a matter of how you draw the arrows and what you think the causal relationships are. Same thing here. Like I named this node collider and I made it a collider because it's going from like X causes that thing and Y causes that thing. So maybe that's being in the NBA. If I adjust for it, it will yell at me and it'll mess up the relationships. So yell, all of the arrows there turn pink. That's bad. So we don't want to adjust for collider. But that's only a collider because of how the arrows are. If I switch this arrow to there, it's now a mediator. and it's fine. It's not messing anything up. So yeah, the way it knows that is it's just following the rules of how these DAGs work. It's not doing anything magical. You can do all of this without Daggity. Um, it's just, this helps simplify things. And then we only want to control for backdoor factors. If you care about the causal relationship between X and Y, then yes, you only want to adjust for backdoor factors. There are situations, especially like in the machine learning world, or if you're trying to make predictions of stuff, where it's okay to just throw in every single variable and just have a massive kitchen sink model. Because in that situation, you don't really care about causation. You're just trying to predict the best way of, or you're trying to figure out the best way to predict your outcome. So like Netflix does this. It tries to guess what you want to watch next. And so it has a whole host of variables that it throws into a fancy model, like the time of day, the day of the week. It tries to guess your mood. It tries to guess all sorts of things. And so it has this massive model with like 10 billion different variables that it throws in there to predict your next movie. Um, if they cared about the causal relationship between the time of day, so like if you're trying to watch a movie at 11 p.m., and the movie you choose, then that's going to be a causal arrow that you care about. And then you're only going to isolate, or you're only going to adjust for things that are backdoors. You want to isolate that one relationship. And so you don't want to adjust for everything in that situation. But if you're just trying to predict stuff, then sure, have a massive kitchen sink model and just throw everything at it, because you don't care about causation. But if you do care about causation, then only adjust for the backdoors so you can get the relationship isolated. Cool. All right, so let's talk about randomized control trials really quick. These are easy because we are fairly familiar with them, because of like TV shows and medical trials and stuff. We all know what the idea of a double-blind study is. So randomized control trials are kind of the stereotypical experimental trial where some people get treatment and some people don't. And the way you find a causal effect in a randomized controlled trial is you basically find the average outcome in the group that got the treatment and the average outcome in the group that didn't get the treatment and subtract them. And then that is your total effect. And that is your causal effect. That's how RCTs work. Analyzing them is like fairly easy because you don't need any fancy regression models. You don't need anything. You can analyze an RCT just in Excel. If you can figure out the average of one group and the average of another group and subtract it, you have your causal effect from an RCT. The reason these are so magical is that randomization takes care of the selection bias. If you randomly assign people to participate in the program, then they're not going to self-select into it, which means the people who need it the most aren't going to purposely seek it out, and it's going to have more of an effect for them. And so it kind of balances out on average throughout the population. It also makes it so that differences in pre-treatment characteristics don't really matter. So if you have a treatment group with some old people in it and some young people in it and some middle-aged people in it, the effect is your treatment's going to have different effects on them. But you're also going to have a control group with some old people in it and some young people in it and some middle-aged people in it. And so any differences you have between those groups kind of get wiped out, and they're roughly about the same. Even if they're not quite the same, on average, they're going to be about the same because of randomization. Okay. There's this idea, a popular idea, and you also have noticed this, a few of you, that RCTs are kind of the gold standard of science and the gold standard of program evaluation. That if you have an RCT, then that will prove causation, and that's like the best way of knowing if something has a causal story. And sure, that is neat. RCTs are great, but they're also extremely limited. JPAL, for instance, the Poverty Action Lab, they do all sorts of cool RCTs in the field. They do experiments in like Kenyan villages, and Ugandan villages, and Bolivian villages. But the issue is they do these experiments with like 600 people in Bolivia, and then they say that will fix poverty, and it won't. You're very limited in kind of the generalizability of your RCTs, because it's very limited. Like your audience or your participants are very limited as well, and so the ability to make generalized inferences from an RCT is kind of more limited when you talk about these social programs. Also, yeah, you see this right now with COVID-19. You'll see new studies come out, and then commenters will be like, "That's not an RCT. I don't believe it." So don't do that, because there are ways of finding causation with RCTs. This idea of RCTs being the gold standard also implies that any RCT is going to be true if you do the experiment right. And that's not the case either. Because again, if you do a small scale RCT in a village in Bolivia, that's going to be right for Bolivia, but it's not going to be right for the rest of the world. In the end, we don't actually care if something is an RCT or not. We don't care if a study is experimental or not. What we care about the most is if the causal inference that we make from a study is valid. If it's valid because it came from an experiment and we know that there aren't any confounders, neat. If it's valid because it comes from an observational study that is very well controlled and has all the confounders taken care of and the relationship between X and Y is very identified, great. That's a causal story. It's just as good as an RCT because we've identified causation. So RCTs are neat, but they're not kind of the ultimate gold standard of all research. Don't worry about that so much. Okay. Also, you can't throw RCTs at everything. We talked about this at the beginning. If you need immediate results, don't run an RCT. It's going to take months to get it out into the field and to analyze the data. If it's unethical or illegal to do an RCT, don't do it, because it's unethical or illegal. Don't do it. Hopefully that's really simple. And like every workshop or every lecture that you hear about RCTs, they always mention this, like, don't be unethical. But then we see studies like the one I mentioned at the beginning where like they randomly assign people to have their utilities turned off for a month. Yikes. Like that is unethical. They ignored this slide. Don't do this. Okay. If we go back to DAG language, the reason RCTs are great for DAG situations is they represent an intervention in a DAG. So if you can randomly assign X here, what that lets you do in the DAG is you get to delete all of the arrows coming into X. So we used to have this Z causing X idea, but if we can randomly assign, or if we can control who gets X here, then that gets rid of that relationship between Z and X. And then that relationship between X and Y is very definitely identified. There's nothing confounding it. So that's one reason why people love this stuff, is because telling a plausible story here of saying X and Y is identified, that is very, very clear in this graph. There's no arrows connecting them. So that's what RCTs let you do in a DAG situation, is delete all of the arrows going into your treatment. So Z is no longer confounding. So that's why it's neat. Okay, so how you analyze these things, it's fairly simple. First, just as kind of a check, you want to make sure the treatment groups and control groups are fairly similar. You don't want a treatment group of all super young people and the control group of all old people, because then suddenly age is going to be confounding that. But as long as they're fairly balanced in age and in income and in gender and whatever, then you're going to be kind of well off with your comparison groups. And then finally, you estimate the difference in the outcome between the two groups. You find the average outcome for treatment, average outcome for control, subtract the two. That's your causal effect. And that's how you analyze RCTs. So let's do that. So go ahead and go to RStudio Cloud. Okay, so in RStudio Cloud, you should see in the Files panel, let's zoom in a little bit, there should be a file called 02RCTs, .r markdown. So that's what we'll go ahead and open up. If you remember from the previous couple sessions, we talked about these R markdown files that let you mix code and text. In this situation, I actually have a fully annotated analysis of this randomized control trial here, which means you can keep this for your own reference later. This has all of the code for checking balance between the groups and then figuring out the actual difference between them. So what we'll do is just briefly walk through this. So if you remember, you have these code chunks. If you want to run all of the code in one chunk, you can click on this play button. So we're going to go ahead and click on the play button for the very first chunk. It's going to load a whole bunch of libraries and load some data from this village. And if we click on village randomized here, it should open up a tab. So it shows us this program here. It was totally fake. I invented this. I just simulated it. So this program was designed to boost people's incomes. And so you can see that some people didn't get the program. Some people did get the program. You can see their pre-program income, their post-program income, their age, and their sex. And that's basically all that we have here. Okay. So what we want to do, first step, is we want to see how balanced those two groups are. We want to see age-wise and sex-wise, are these two groups roughly about the same? So we do have a DAG here. You can do DAGs directly in R. I have the code for it here. We're not going to talk about it because it is a little bit more complicated, but if you run that chunk and look at it, there's our fancy DAG. Yay. But because it's an RCT, we actually get to delete the arrows going from income to program and age to program and sex to program. So it's just this program to the post income that's very isolated, very identified. And so we don't need to worry about confounding because it's a randomized control trial. Okay, so we want to check the balance here. And so what we're going to do is use some code from the dplyr package that we talked about in the very first session, where you get to use these different verbs. We're going to take this village randomized data set, and we're going to count the number of people in the program and not in the program. And then we're going to mutate, which is going to make a new column called proportion, and that's just going to figure out the percentage of people in the program and not in the program. So if we run this chunk, you'll see that 503 were not in the program, 497 were. That's about a 50.3 and a 49.7 split. So there's about half and half. I think that's good. Neat. It's like I invented this data. So now we want to see how balanced everything is with sex and age and pre-income. So we're going to use the same dplyr syntax here. We're going to take the randomized village data set. We're going to group it by program. So that means we're going to make a group of people in the program and a group of people not in the program. And then we're going to find out the average sex, age, and income in each of those groups. So if I run this chunk, you'll see we have this here. People not in the, so it was 58% male not in the program, 60% male in the program. That sounds about balanced. Age, about 35, sounds balanced. Pre-income, people not in the program at $803. These guys had 801. That's a tiny difference. We can do statistical tests to see if that's statistically significant, but that looks pretty much the same, so I'm not too worried about that. So if you scroll down more, I actually have some code here that shows you how you can visualize the differences in the groups. These are just pre-treatment characteristics. You can use R to do this. You can use Excel to do this. You can use Stata. This doesn't really matter. All we're just seeing is what does the proportion of people in the program and not look like across these different pre-treatment characteristics. And so that's really all we have here is just if you keep running these different chunks, it's just showing you pictures of age, not in the program, pre-income, not in the program, and this looks pretty balanced. Hooray. Okay, so the last thing we want to do is estimate the difference. So we want to find the average income for people in the program and average income for people not in the program. So to do that, we can just use dplyr here. We're going to take our randomized village, group by program. So we're going to have people in the program, people not in the program, and then we're going to figure out their incomes, the average income. So what this shows is people in the program, their average income was $1,280, and people in the program was $1,180. So the difference there, if you just subtract 1279 minus 1179 is $100 or $99-ish. And that is our causal effect. So we can say that this program caused people's incomes to increase by $99 on average. And that is how you analyze an RCT. Fairly easy. If you want, you can actually do it with regression. So if you look down this very last chunk here, we'll run a regression model explaining after program income using the program. And this will show the same effect at $99. So if you're in the program, your income goes up by $99. and that is a randomized control trial. This is just very generic R code. The way you analyze this is not tied to R in any way. You can do this with Excel. You can do this by hand on paper. If you can just figure out the average outcome for the two groups, then you have your randomized control trial estimate. And that is fairly easy to do. So go ahead and we'll take a 2-minute break. Ask any questions in the chat and we'll answer them in 2 minutes. And then we'll move on to proving causation using DAGs and adjustment and regression. So I'll see you back here in 2 minutes. Ask questions. Okay, so Jonathan Smith has a question about this weird percent greater than percent symbol. That is an R thing. We talked about it in the very first session, if you were part of the very first session, where it essentially lets you concatenate different functions and feed them into each other. So if you look at the code, what we have is we're taking this village randomized data set, and then we are feeding it into a function called count. And then we're getting a count of the programs. And then we're feeding that into this function called mutate, which adds a new column. So the way you can read this is and then. So we're saying take village randomized and then count it and then add a column to it. So this is from the very first session here. What it essentially does is it takes this thing and puts it as the very first argument in the function that comes after it. So you're just like in this situation, you're taking this data set called gapminder, feeding it into this filter function, and then isolating it so it's just showing Canada. These two here are the same thing. So like filter gapminder country equals Canada versus gapminder and then filter so country equals Canada. Another way of looking at it is right here. You can have nested functions. So if you look at this, this is me, and I'm waking myself up at this time, and then I get my woken up self out of bed, and then I get my out of bed woken up self dressed, and then I leave the house using the dressed out of bed woken up version of me. And that's really hard to read because it's all nested like that. This is what it looks like using these percent greater than percent symbols, or R calls them pipes. So you're taking me, waking up, and then getting out of bed, and then getting dressed, and then leaving the house. So that's what that is. If you weren't here for the first session, the materials are online. Tyler mentioned them. There's also, I have a website here that I'll put into the chat where it has the materials for all 3 sessions with all the slides and stuff here. So you can also go there and see them. Also in RStudio Cloud, because this is an R Markdown file, if you click on knit at the very top, it will run that whole document, where it'll run each of the chunks and get all of the code output for each of the chunks, and then create this very nice HTML file walking through the whole process of analyzing the data. So there's the checking balance, there's the pictures, there's the causal effect, everything's in there nicely. So that is how you analyze RCTs with R. Neat. All right, so next, let's talk about confounding stuff using regression. Okay, so RCTs are easy, as we just saw. But once we get into this DAG world, it's going to get a little bit trickier. So I already mentioned that you can adjust for things by just including them in a regression model. So if we have that education to earnings example we've been talking about, based on the DAG, it said we should control for background and year and location. I think were the 3. And so if we ran a regression model with those 3 things in there, in theory, that should give us the causal effect. The issue with that, though, is if you just control for those things in a regression model, that will only isolate that causal effect if the relationship between all of those other confounders is linear. So that means the relationship between year and education and year and earnings has to be linear, and there can't be any curves in it or anything like that. Once you get into curvy relationships, just controlling for things doesn't work. And my assumption is that everything in the world has some sort of weird curve to it somehow. And so just throwing stuff into a regression model is not going to necessarily give you the most accurate causal effect. Conceptually, if you want to think of closing backdoors as just including things in a regression model, that's great. That's an easy way of remembering, I need to control for these things, I need to adjust for these things. But in actuality, you have to do some fancier things to make adjustments that take into account weird, curvy, nonlinear relationships. And so one way of doing that is with something called matching. So if you look at this picture here, notice how there's some relationship between education and some outcome. There are some people that got a treatment and some people who did not. And so the blue dots are people who are in this control group. It's not an RCT. It just means that they didn't get the treatment, and the red dots did get the treatment. So here, if we just ran a regression, it would draw a line somewhere between those dots, but it's not going to be the most accurate line. What could we do to make the best comparison between red and blue dots here? Go ahead and in the chat, tell me what you think we could do here to make it so that we're comparing just red and blue. Do you see any patterns in there that we could do or that we could deal with? Okay, so we say eliminate outliers. So we see two different groups here of control of people who didn't get the treatment. They're not necessarily outliers. An outlier would be like if somebody had like 50 years of education, that's going to be way out there and all by themselves. In this case, there's a big cluster of people with high school education, and there's a big cluster of people with 30 years of education. So it's not necessarily outliers, but Carol's idea is restrict the range. So in this situation, we don't want to look at this group of people. We don't want to look at this group of people because there's no treated people in either of those groups. Nobody got the program that people in high school or with super high degrees. The only people that got the program or didn't are this cluster up here. So what Matthew here says is match on education level. We want to compare people who have about the same education level. So we want to find this person here with 15 years of education. They got this program, they got this treatment, but there's someone very similar to them, this 16-year person here, they're roughly the same education-wise. And so if we could match those two, that'd be cool. These two people are pretty similar. Those two people are pretty similar. This whole cluster is pretty similar. So if we can restrict the data to just that world up here and ignore these people here, not that they're outliers, but because there are no people that got treatment in those groups. And so we don't really want to deal with that. And so if we can do that and match the treated and the untreated pairs, then that will let us find kind of a more accurate view of the effect of the program. So the general process for matching is this two-step process. Here, first you have to pre-process the data, which just means you do something to guess how people got the treatment. So if we go back to our picture here, we can, not knowing anything about this fake program I invented here, you can guess that this treatment was given to people with a college education. It was not given to people with high school education. It was not given to people with like 30 years of education. And you can guess that just by looking at the outcomes here. So we can get rid of that. So yeah, we should ignore the treated people. Not necessarily. We'll see. There are ways of statistically figuring out who you can ignore. Generally, you don't want to ignore any of the treated people because you care about them. They got the treatment. You just want to find a comparable person to each of them. So in this situation, without doing any math, we can just say, get rid of those. This whole group up here looks pretty good. But you can be more systematic than that, which is this pre-processing idea. And the neat thing about this is you can use what you know about the DAG to inform this. So if you know that this program was determined by age and by education, then you can figure out using age and education who got the program and who didn't. This is where you make the adjustments. So if we go back to the education and earnings example, where year and location and background were all confounders, if we match using those three confounders, then that will let us get the best comparison groups between people with people with treatment and people without treatment. And so that is where we do the adjustment, is when we're trying to find the matching groups. And then you estimate, and then you use that new pre-processed, trimmed, matched data to then figure out the difference and the causal effect. Okay, there are different ways of doing this. This picture right here, we can just do the naive example of just saying, get rid of that cluster, get rid of that cluster, call it good. In real life, you can't actually do that very well unless it's super obvious like that. So there are a couple different methods. There's one called nearest neighbor matching, which is what it sounds like. You try to find dots that are the nearest neighbors to each other based on a whole host of other factors. They have fancy names like Euclidean distance and Mahalanobis distance, and we don't care about those differences. It's just ways of figuring out the distance. And then there's this idea of inverse probability weighting, which is figuring out, instead of throwing away data, it lets you get like a numerical weight to how similar or how different people are, and then you can use that. So we'll show an example of both of those. So nearest neighbor matching is where you just want to find observations that are very similar to each other based on the confounders. Okay, so here's our DAG. We have treatment leading to some outcome, but education is confounding that and age is confounding that. So according to this DAG, we need to control for age and education. But we don't want to just throw that into a regression model because there might be curved lines, there might not be a linear relationship. So instead, we're going to adjust for these things for age and education by matching. So here is another example of we'll just match on education here and age. So these are our two confounders. So what we want to do is find points that are very similar to each other in both age and education. And the way you do this is you basically find the nearest neighbors. That's this whole idea of nearest neighbor matching. So these 2 points right here, that's a good nearest neighbor match. They are very similar in education, very similar in age. These 2 points here, that's probably a good match too. That point and this point, that's probably not a good match. So if we use what is called Mahalanobis distance or Euclidean distance, it's some fancy mathy way of figuring out nearest neighbors, this is what we end up with. These pairs are the observations that are most similar to each other based on age and education. And so if we limit our analysis to just them, and then we try to find the causal effect of this program just on this smaller data set, we have now adjusted for age and we have adjusted for education. And all we have to do is figure out the average of the outcome for the treated group and for the untreated group. And it's basically like a randomized control trial. Because we made the adjustment for age and education, we closed those backdoors. Okay, so that is how this nearest neighbor matching thing works. In this situation, that's two different variables. You can match based on a whole bunch. It's just impossible to graph it then, because then you're in like 4 and 5 and 6 dimensions. And so that's why this is just a 2-dimension example, just education and age. But now all of these points are very similar on those confounders. And so now we can have valid causal estimates based on that. Okay, so that is matching. So with this question here, should you ignore the treated people outside of the 15 to 25 range? Most likely not, because the algorithm is going to say it's going to try to match those people who are outside of those range or outside of that range with somebody who's very similar to that range. So it's going to try to use the whole data set and try to find the best matches in everything. And so it'll throw away some stuff, but it'll also try to pair every treated person with an untreated person. You can also change it so it doesn't do a 1-to-1 match. In this situation, this is 1-to-1. But you can also say you can have many to one. So you can say this red dot is close to that person and it's also close to that person. So keep both of those blue dots. So it just depends on what you tell R to do or what you tell Stata to do. Okay, so the other way of doing this is using something called propensity scores, which is essentially using a model to predict, to generate the predicted probability of getting treatment. This goes beyond the workshop, but essentially you're using what is called a logistic regression model. You can also use machine learning. You can do all sorts of stuff. You're just trying to predict, or you're trying to get a probability that somebody is going to be in the treatment group. So if you look at this example here, this is trying to predict transmission, if it's automatic or manual based on miles per gallon. And so what we have are these propensity scores. This is the probability that you are a automatic car. And so some of these cars, this row number 3 here, they have a 60% chance of being an automatic car. So that's pretty high. This car right here has a 10% chance of being an automatic car. So they're probably not an automatic car. So that's basically what we're doing, is using fancy stats to generate a propensity score, the probability score of being in treatment. And then we use that score to weight things, to weight the observations and say that things are more important or less important. And so, briefly, to talk about, before we show the inverse probability weighting stuff, we need to talk about weighting in general. This is something that happens all the time, especially in polls. Presidential polls right now have weights all the time. So let's say you do a survey, and you know that in the whole world, 30% of the population is young, 40% are middle-aged, and 30% are old. You know that from the census or from something. And you do a survey, and you find that 60% of your sample is young, and only 10% are old. You could just give up and say, oh no, this doesn't match the population, or you can reweight these things. You can make the young respondents be less important, and you can make the old respondents be more important. Because there are more old people in the world than you picked up, and there are fewer young people in the world that you picked up. So what you can do is, if you divide, you can create this weight here. So you're saying there's 30% in the population, we picked up 60%, and so we're going to count every young person as only half of a response. And we're going to count every old person as 3 responses, just to kind of give them extra weight. So that's this idea of weighting, making some observations more important, some less important. Okay, why this is important for matching and for this propensity score stuff is you can use the propensity scores to weight the observations based on how weird or unexpected they are. So let's say you run a model, and this is the actual math equation for it. You find the probability of, or whether or not they're in the treatment group, did they get the program, and the probability that they got it. And then you add this fraction here, the inverse of that probability. And we'll show an example of this. So if we go back to this example here, this is the probability of being a manual car or an automatic car based on your miles per gallon. So some of these observations are weird. This car right here had a 70% chance of being automatic, but they weren't. So that is weird. And so we're going to give it a bigger weight because that's kind of a rarer thing to see. This observation here only had a 10% chance of being automatic, and they weren't. So that's pretty standard. We don't care about that. So it's unlikely to be manual, and it's not. So we're going to give it a lower weight because it's not weird. So what this lets us do is, if we go back to this picture here, when we did the matching, we got rid of a whole bunch of observations. So these two matched. They were probably the nearest neighbor matching, and so we got rid of the ones around it. Instead, with this inverse probability weighting, we're saying this red point is kind of weird, because it's in this neighborhood of people who are older and have higher education. They didn't get the treatment, but this red dot did. So we're going to give that red dot some more importance. That's a ton of importance. These red dots down here are smaller because that's not as weird, because they're pretty similar to these other blue dots. So really, this inverse probability weighting thing is just a measure of how weird and unexpected something is. And then we can adjust using those weights in a regression model. The nice thing about this is we're not throwing away any data. When we did the nearest neighbor matching stuff, that blue dot was gone. These blue dots were gone because they weren't matched with any of the red dots. When we do this inverse probability weighting, that just lets us keep everything. And we just say some of these dots aren't important at all. Some of them are super important. And we'll just incorporate the importance into the model. The way the adjustment comes into play here is when you generate these propensity scores, or the probability that you got treatment or not, you use the confounders to generate those propensity scores. And so we're going to predict whether or not somebody's in the program based on education and age, because those are our confounders. If we had other confounders, we could also throw those into the propensity score model. And then we use kind of this data set and these weights to figure out the causal effect in the end. Okay, so we're going to do this with R now. So if we go back to RStudio Cloud and open up number 3 here, we have a matching data set. So go ahead and run this very first chunk. It's going to load a data set called MathCamp. So in this situation, this is, again, fake data that I made up. It has a causal effect in it because I built it in, but we're going to find it using observational data. This is not an experiment. The idea here is that some MPA program, MPP program wants to encourage people to do well in math, and so they offer a math camp program before the actual master's degree starts, and then they measure the effect of that program after graduation. So that's what we're looking at here is final grade after they graduate for some test they take. It's made up numbers. Whether or not somebody participated in math camp, and then some confounding factors here, their undergraduate GPA, their GRE scores, other things like that. The important thing here is this is not experimental. The people who did math camp chose to do math camp because they needed it. They self-selected into it. So anything we calculate here is going to be biased if we figure out the average score for people in math camp and people for not in math camp. So this is good because we want to adjust for all of the confounders so that we can isolate that causal effect. Okay, so if you scroll down through the document, you can see the details of the program. You can actually read it later if you want. So what we're going to do, I built in a causal effect of 10. So with all of these different methods, we're going to try to see if we can find 10. That is the truth. If we look at this, here's the DAG. You can see there's these different confounders. The GRE score that you have is confounding. Your undergraduate GPA is confounding. GRE verbal is not confounding because you see there's no arrow between your GRE verbal score and math camp. So our confounders are your quantitative GRE score and your undergraduate GPA score. Those are the two things we need to adjust for. Okay, so what we're going to do is do some analysis here. We're going to do a naive difference in means. So this is the correlation is not causation idea. We're just going to figure out the average score for people in the camp and average score for people not in the camp and figure out what the difference is. And so if you run that, this involves a little bit of math. We'd have to say 1180 or 144 minus 137. I can't do that in my head. So if we just do this with regression, we can see that being in math camp boosted your final grade by 6.5 points. That is not true because there are confounders here. This is when at the beginning I said never say correlation is not causation because it's not all the way true. This is a situation where correlation is not causation. We're not even trying to adjust for confounders. We're just saying that people in math camp had higher scores. But people in math camp also needed math camp and they went and did it and they sought it out on their own. So this is not entirely accurate. So what we want to do is adjust for our confounders. So we're going to adjust a few different ways. We're going to adjust the simple way here that I told you not to do, but in this situation it works because it's fake data. We're just going to include our two confounders, undergraduate GPA and quantitative GRE score. We're just going to include those as variables in a regression model and see if it works. So remember the true point difference, the true effect was 10. So if we run this, we can see being in math camp causes you to have a 10-point higher score. That works because it's fake data and there's nothing nonlinear there, but that's essentially what just happened. We got rid of the effect of undergraduate GPA, we got rid of the effect of GRE scores, and we're left with just the math camp effect. And that's our causal effect. And so based on the DAG, if we believe that it is right, we can now tell a causal story just using regression. We don't have an experiment. We just adjusted for the confounders, and based on observational data, MathCamp caused a 10-point increase, which is pretty magical. Okay, so why did I define the model and then call it Untitled? That's just an R thing. I could, if you just select this and run it, it will show the model results directly here. I'm saving the output from that model function to this object called model adjusted, and then I can do stuff with it. So if I just run model adjusted, it'll show the same thing. Tidy, it converts this thing into a data frame. So it converts it into this thing with rows and columns. And that's nice because then you can later plot it and you can do other stuff with it. So it's just a way of showing it in a table. But really all you need to do is just run this LM thing and there's the 10-point increase. Okay, so that is adjustment with regression. That is like super magical and mind-blowing to me. I've been teaching this for like 3 years now and I still like, this is so cool because now you can talk about causation just like using regression when you were always taught don't do that. It only works if the DAG is well defined and it only works if there's nothing nonlinear in there. But there it is. We see the 10-point thing that I built in and it's right there. That's so cool. Okay, we can also adjust using matching, where we're going to try to find the nearest neighbors and find a smaller data set of just the people who are treated with the people who are close to them who are untreated. So to do that, we can use a function called matchit. And the idea here is we're going to use the confounders to figure out the best match. So notice here, we're using undergraduate GPA and quantitative GRE scores as the way to match. If we had other confounders, we'd include them here, but we just have these two. So if you run this chunk, it takes a couple seconds. There it goes. It just matched everything. If you look at the output here, it shows a whole bunch of information. It shows the balance of the different variables across the matched groups. You can look at that to see if the match was good. If you look down at the bottom of this, it shows that 365 control groups were matched with 818 treated groups, and 817 observations were not matched. And so it's going to throw those away. So we're just going to be left with these two groups there. Notice how that's not one-to-one. That's because I think I said don't be one-to-one. Yeah, replace equals true makes it so that it's not one-to-one. If it was replace equals false, then it's going to be exactly one-to-one matches. Okay, so what we want to do, if you go to the next chunk, we're going to make a new data set based on that matched data. So if you notice, the original math camp data set was 2,000 people. Now we only have 1183. So we got rid of like 900 observations based on this matching. Then the last thing we're going to do is run a model. Instead of including the confounders, undergrad GPA and quantitative GRE, we're just going to look at the effective math camp. The reason we're not including the confounders is because we already did stuff with them. We used them to figure out the matched data set that we're now using. So we don't need to use them again. So now if we run this, there's our effect, 8.3, which is better than the 6.5 that we had with the correlation isn't causation thing, but not 10. We want it to be 10. One of the nice things that happens with matchit, if you look at the math camp matched data set, it actually gives you a column called weights that's based on kind of like the inverse probability weighting, how important the different points are. So if we incorporate those weights into the regression model with the matched data, it should actually give us a better, more accurate estimate. So if you come down to this chunk here, you can see we're going to find the effective math camp on final grade using our matched data, but we're going to use that weights column. So if we run this, it should be almost 10. Yep, 9.8. Cool. So based on matching, we were able to find a causal effect of 10 using the confounders to match, which is cool. Then the last one is this inverse probability weighting idea. If you scroll down, if you want later, you can read all about logistic regression and predicted probabilities. We don't care about that so much. So if we scroll down to about line 211, 210, with inverse probability weighting, what we want to do is figure out the probability that people were in the program. So we want to figure out the probability that somebody participated in this math camp based on the confounders. So based on undergraduate GPA and GRE quantitative, what is the probability that they participated in math camp? Okay, so if we run this, that will build the model that's going to guess if they participated in math camp. And then this next chunk will actually make the predicted probabilities. And if you look at it, you can see, so this very first person, they did not participate in math camp. The probability that they would have been in math camp was only 10%. So that's pretty expected. They weren't going to, That's a very low probability they were going to, and they didn't. This person didn't participate, and they had a 37% chance of participating, so it's still low. This person participated, they went to math camp, and they had like a 56% chance of participating, so that's probably accurate. So you can go through and look at all of the different people to see how likely it is that they would participate and whether or not they did. But what we want to do next is figure out the weirdness score. How weird is it that this person that only had a 10% chance of going to math camp didn't go to math camp? That's probably not that weird. So we use this formula here to figure out the weirdness score, or the inverse probability weight. So if you come down here, we're going to run this chunk, and it will create our inverse probability column here. So this is the weirdness score. The lower it is, the less weird it is. So all of these are pretty low. If we actually look at the full data set, which is called MathCamp IPW, if we scroll down, there's a person, they have a 6. So that means the probability of participating in camp was 16%. So there was a 16% chance they were going to go to math camp, and they did. So that's weird because that's really low. So we want to give them a higher weight, is what's happening there. So finally, we have our weights. We're going to figure out the estimate. So we're going to say math camp explains final grade. We're going to use that inverse probability weight data, and we're going to use that weirdness column to weight each of the observations. And so if we run this, there's our 10.87 effect. It's not exactly 10, but that's pretty close, and that's better than the 6.5. So that's it. That's how you use inverse probability weighting and matching. Again, the whole concept behind this is we're just saying we're using our confounders to guess why people are in the program, and then that lets us adjust. And then once we have kind of the adjusted data of people who are matched or people who are weighted, then whatever we do to calculate the causal effect should be isolated and causal. We've gotten rid of the confounding, and we're left with just math camp causing grades, or X causing Y, or education causing earnings. And we've gotten rid of everything else through matching and through inverse probability weighting, and sometimes with regression, but it rarely works with regression. Okay, so that is how you do it. This is super magical and awesome. Again, you can knit the document and keep it for future reference. You can also download all of this stuff. In RStudio Cloud, you'll notice there's a PDF here called Causal Inference. This is a book chapter I wrote for some textbook thing. It's basically a summary of this whole idea of DAGs and adjusting for things, and shows examples of making adjustments using matching and inverse probability weighting and stuff like that. So you can also use this as reference in the future. Cool. So go ahead and take a 2-minute break and ask any questions you have in the chat, and then we'll come back to a couple of final econometrics type things that we can use for finding causation. And I'll see you back here in 2 minutes. Okay, welcome back. We have some good questions here from Janelle. Yes. So first with the matching, are there any major drawbacks for doing one-to-one versus one-to-many? The main drawback is just data size, or the number of observations. So if you do one-to-one matching, like in that math cap example, I think there are only 300 people who got the treatment. And so if we do one-to-one matching, then we're going to only have 600 observations in the end, which is probably fine for regression and finding like statistical significance. But if you have like a smaller data set that only has like 30 people who got the program and 100 that didn't, you're going to lose a whole bunch of observations if you just do one-to-one. You'll be left with 30 plus 30, 60. And so, yeah, you don't want to, like, that's actually why inverse probability weighting is generally better than matching, because you don't throw away any data. You just assign the weirdness score to each of the points and incorporate everybody instead of throwing stuff away. For the confounding here, this question about even if you include all the confounding variables, there's still going to be unobservable characteristics. Yes. So that's the trick here. And people who don't like DAGs, there are a few, say like it overly simplifies things and you're missing stuff in the DAG. And so my response is, yeah, you are. Include more stuff in the DAG. And like, so if we go back to this example here, we have year, location, background all influencing this relationship. We just said something is influencing location and background. Sure. Um, throw other stuff in there and see what those relationships are. In this situation, this unobserved stuff is okay because it's behind location and background, which we can adjust for. And if we close those off, that unobserved stuff is gone. Like it's not influencing education and earnings because we closed those doors. And so it's not going to influence. If unobserved is down here, if we have a U2 that is influencing education and earnings, and we can't observe it, then, oh no, we can't actually do anything about that because it's not being blocked by other stuff. In this situation, it's okay. It's being blocked off. That's great. That's again, like you really should look up the iOS game. I think they have it on Android. It's called Where's My Water? It's this alligator guy that you draw water through pipes and in the ground and stuff. This is really what you're doing with these things. And so U1 is behind those blocked doors. It's not going to get down the education and earnings. If you have unobserved stuff that is influencing education and earnings in other ways, then you have to do fancier things like instrumental variables identification. We're not covering that at all today. There are other things you have to do, but again, the really cool thing about having a DAG is people can fight you about the DAG. And they say you're missing something, you say, okay, and throw it in there and see if it messes up your confounding relationships. And it gives you kind of a good foundation for talking about your theory. So go DAGs. I am firmly on team DAG here. Okay, so in the last 40 minutes, we're going to talk about a couple econometric approaches to causation, which you can actually do without DAGs entirely. And there are people who do economics all the time who don't even think about DAGs, and this is kind of their way of thinking about causation. You can draw DAGs for both of these things, but we'll just talk about how to do these other ways of proving causation outside of DAGs. The first is this idea of difference in differences. And the idea here is that you can actually use two wrongs to make a right in this situation. So the way we're going to explain this is, let's say, what is the effect, do you think, if you raise the minimum wage? Will wages go down? Will there be fewer jobs, or will there be more jobs? This is a very standard question in economics, very standard question in politics. This is one reason why some politicians don't want to raise the minimum wage, because it will cause job loss. And so economists have done experiments, or natural experiments, to figure out if there is a causal effect of raising minimum wage on the number of jobs that exist. So according to economic theory, if you raise the minimum wage, the price of labor is higher, and so the quantity should go down. That's supply, demand, economics stuff. But we can actually measure this out in the world. And so in New Jersey in 1992, they raised their minimum wage from $4.25 to $5.05, but other states did not. And so what economists did back in the 90s is they said, this looks like an experiment type situation where one state does something, the other state doesn't. And so if we can find a comparable state to New Jersey that can be the control state, we can see if there's a difference in the number of jobs that exist because of the minimum wage change. So what they did is they looked at Pennsylvania because it's next to New Jersey. So there's a couple ways of looking at this. You can look at before and after just in New Jersey. So you can say the average number of fast food jobs in a fast food restaurant in New Jersey before the change in minimum wage was 20.44. After, it was 21. So based on this, just before and after in New Jersey, the difference is like half a job that was increased because of the minimum wage change. So that looks promising if you care about raising the minimum wage. But you can't just look at before and after because you don't have a control group. So we want to compare New Jersey to some other states. So we can compare it to Pennsylvania because it's right next door. And so in Pennsylvania, after the minimum wage was changed in New Jersey, the average number of people working in a fast food restaurant was 21. In New Jersey, it was also 21. So there was a tiny difference, a tiny decrease in New Jersey. So is that the causal effect? No, because we don't know what happened in Pennsylvania before the change or New Jersey before the change. So if we just look at before and after, you can't tell if any of the changes happened in New Jersey just because of natural growth. Maybe everybody had more jobs and the minimum wage had nothing to do with it. If you just compare treatment and control, then you also can't tell if it's because of natural growth. You can't tell if Pennsylvania was also just growing by itself and had lots more jobs and New Jersey also did. So you can't just do before and after or just treatment and control. You have to do both at the same time. In the DAG world, this is what the DAG would look like. Minimum wage causes jobs to increase or decrease. Time, so the year that you're in, causes the minimum wage to be some level. So if you're before the change, it's going to be lower. If you're after the change, it's going to be higher. And that's also going to change the number of jobs that exist just because of trends in the economy. So time is a confounder. Being in New Jersey is a confounder. If you're in New Jersey, you get the minimum wage increase, and maybe there's some trend in New Jersey jobs. If you're not in New Jersey, you don't get the minimum wage change, and you get some sort of trend in jobs. So you have this dual confounding here. So according to DAG logic, we need to somehow adjust for time and adjust for being in New Jersey. And then that should isolate the effect of minimum wage on jobs. Another way of doing this is combining the before and after with treatment and control. And so if you make this 2x2 matrix here, if you can figure out the average number of jobs in the treatment, so average number of jobs in New Jersey and the average number of jobs in Pennsylvania before the change in minimum wage and after the change in minimum wage, you can actually do some math here. If you find, so you figure out the difference in New Jersey before and after, the difference in Pennsylvania before and after. And if you find the difference in those differences, so this B minus A minus D minus C, that corner right there is the causal effect. That is incorporating both the difference in treatment and control and before and after. What this looks like is here. So we already saw these numbers here, where New Jersey before the minimum wage had 20.44, after had 21, so there's our 0.59. Pennsylvania before had 23, they went down after. If you combine these two, so 0.59 minus negative 2.16, the causal effect is 2.7. So you can say that the minimum wage increase caused restaurants to hire 2.7 more people. And that is a causal story because we've taken care of the before and after, the time node, and we've taken care of being in New Jersey. So we adjusted for both of those things, and we're left with the causal effect. What this looks like graphically is this. So you say, here's our comparison. So that's Pennsylvania before and after. The treatment group, that's New Jersey. What you essentially do is you say, had New Jersey not raised their minimum wage, this is what they would have had. This is the number of jobs they would have had. But because they raised the minimum wage, they went up higher. And that difference right there, that difference in differences effect, that is the causal effect of raising the minimum wage. Each of these points are actually points in that 2x2 table here. That's A, B, C, and D, which is the same as right here. So you can actually figure this out based on this table here. If we were in my actual causal inference class, I would have you manually figure out all the values for A, B, C, and D for some situation, and then subtract them and then subtract them again. And that's really, really tedious. I'm not going to make you do that because it's awful. And you can use regression to do it for you instead. The way you use regression to do it is use an interaction term, which if you remember from your stats classes, it's when you multiply two things. We don't have time to go over the logic behind it, but essentially that's what you do. And then the coefficient that appears in front of this group times time coefficient or term, that is your causal effect. And so if we ran this in R, whatever coefficient we get there is going to be the causal effect. Okay, this only works if you can assume that New Jersey would have followed the same path as Pennsylvania without the treatment. And so this is where people will fight you in a seminar about your estimation. They'll say, maybe it wasn't parallel. Maybe New Jersey would have just naturally had that many new jobs without the minimum wage increase. And so you have to argue that they were probably going to be similar. And that's why you want to choose a comparison group that is fairly similar. You don't want to compare New Jersey with like Montana, because they're going to have wildly different trends. But because New Jersey and Pennsylvania are right next to each other, that's probably a plausible story. Okay, so let's do this in R really quick. Does this only work for linear models? Yeah, kind of. It mostly yes, because of this linear trends assumption. If this comparison group is curving upward and the treatment group is also curving upward, then that works. But like, it's going to get really messy and weird with the curving. So economists will still just throw it into a linear model and they'll say that it's fine. And arguably it's okay. There's mathy reasons why it's generally okay. But it's more difficult to tell a plausible story and people will fight you on it. But you can do it. Okay, so if we go to RStudio Cloud, go to the number 4 here, this diff and diff. So this has, again, it's fully annotated here with all sorts of stories. This is actual real data. This is in 1980, Kentucky changed the policy where if you were getting workers' compensation benefits, you could only earn so much money in a year. And if you earned more than that, then you lost the workers' compensation benefits. And so what they did in 1980 is they raised that limit. And so you could earn more money. And they were concerned that people would be on disability for longer because they would get more workers' compensation. And so what they wanted to measure is the outcome here we care about is the duration of workers' compensation benefits before and after this policy change. Okay, so we're going to run this first chunk here to load the data. Notice it's called injury here. It's got a whole bunch of different columns. There's probably documentation for what they all mean. Some of them are pretty self-explanatory, like hospitalized, or maybe that's, I have no idea what that means. Probably something related to, were they hospitalized because of their injury? That's probably it. Are they high earners? This is after the change or before the change. So if it's 0, it's before the change in policy. If it's 1, it's after the change in policy. So that's what those columns mean. This next chunk, we're just going to extract Kentucky. They also included like Michigan, I think, in there. So we just want Kentucky. We can look at it really quick. If you run some of these chunks, this just shows us some exploratory stuff. This is the duration in weeks of unemployment. So most people are not unemployed for a very long time. There's some people up here like in the 180 weeks range. That's a long time. What is 80 divided by 52? That's like 3.5 years of unemployment. Neat. If we log it, it makes it less skewed. So there's kind of the logged weeks of being unemployed. So this is all just background stuff just to look at what the data looks like. We don't care about that so much. What we care about, though, is we can either do this diff and diff by hand, and this is where I have my students actually calculate high earners before 1980, low earners before 1980, figure out their average number of weeks of unemployment, and then do all of the awful math to figure that out. I have the code here for it, so if you just run that and run this, it will show you the causal effect of changing that policy is it increased unemployment duration by 0.19 logged weeks, which is a nonsensical number. But because it's working with logs, we can actually interpret that as like a percentage. And so it caused a 19% increase in the length of unemployment, is what that's showing. But that's miserable, figuring out all of the A, B, C, D squares and then subtracting them all. So this is where we can do the regression version of it, where we want to say high earners, so whether or not they're high earners or not, after 1980, and then the interaction between the two. If we were doing the New Jersey, Pennsylvania thing, this would be New Jersey, yes, no, after the minimum wage increase, yes or no, and then the interaction between the two. And if we run that, there's that 0.19 that's the coefficient for that interaction term. And that's the final estimate there. The nice thing about doing it regression, or doing it with regression instead of doing this miserable fill in all the cells thing, is you can put in other variables. It's just a regression. And so you can throw in other confounders. So if your DAG says there's other things that influence both um, being a high earner and the number of weeks that you're on unemployment, you can include those controls as well. And so that's what you see later on here. Here's this big model. We threw in a whole bunch of other control variables, but we still have our difference in difference estimation, and that's our causal effect. And now instead of 0.19, it's 0.16, 0.17, because some of the causal effect was taken up by the confounders, but that's still our causal effect. So that's difference in difference analysis. It only works if you have a situation where you have kind of a treatment group and a control group that is plausible, and you have a before and an after. It wouldn't work with that education earnings situation. It wouldn't work with the math camp situation that we looked at earlier, where we threw stuff in the regression, or we did the matching or the inverse probability weighting. Difference in difference only works in kind of this specific situation where you have treatment control before, after, figure out the difference between those differences, and then that's your estimate. Again, if you click on knit, it should create a complete document here that walks you through all of the different steps here. Stata does the same thing. Really, this is just regression. So any program that has regression in it, as long as you can do an interaction term, you can figure out a different diff estimate. So that's difference in differences. Let's go ahead and take a 90-second break. Ask whatever questions you have in the chat, and then we'll finish up with regression discontinuity, which is one of my favorite types of finding causal inference, just because it's so neat. So see you back here in a minute and a half. Ask your questions. Okay, welcome back. So the last way of finding causation that we'll talk about is this idea of regression discontinuity. And this is one of my favorite ones, as I mentioned before the break, because it's just like so neat and so convincing. Diff and diff is less convincing to me, and less convincing to lots of people, because it rests on the assumption that your fake comparison group is very, very similar. So with the New Jersey and Pennsylvania idea, you have to prove to your audience that Pennsylvania is basically New Jersey without the minimum wage increase. And that's really hard to prove. And people will fight you on that, for like, they'll do all sorts of fighting about that. And so it's messy. There's other reasons why diff and diff is messy mathematically. It's still wildly popular, but it's a very specific situation you have to look for out in the world to be able to estimate it. Regression discontinuity is also a very specific situation that you have to find out in the world. You can't just throw anything at it, like the math camp idea that we did before. That doesn't work with regression discontinuity. But when it does work, and when you do see a discontinuity in the world, it is like super convincing. And people love this stuff. And the reason why this works is because of the idea of arbitrary cutoffs that exist out in the world. All sorts of policies have some sort of cutoff that give you access to the program or not access to the program, where you have to meet some threshold. So if you're above some threshold, you get in the program. If you're not, then you don't get in the program. You see this all over the place. For instance, here, this is the poverty line in the United States. We have 138% of the poverty line, 150%, 200% of the poverty line. These numbers here determine if you get Medicaid. If you're below 138% of the poverty line in states that have expanded Medicaid, then you get to have Medicaid. If you don't, then you don't. With Affordable Care Act subsidies, if your income is between 138% and 400% of the poverty line, then you get subsidies for the Obamacare exchanges. If you don't, then you don't. So if you're at 137%, you don't get the subsidies. You get Medicaid in theory, unless you're in a state that has not expanded, and then you get nothing. Getting CHIP, the Children's Health Insurance Program, that's 200%. So if you're at 201%, you don't get CHIP. If you're at 199, you do get CHIP. SNAP benefits, food stamps, free lunch, they also have kind of a strict line. If you're before that line, you get it. If you're after that line, you don't get it. So that's this idea of a discontinuity here, where there's some rule that exists in the world, and some people get the program and some people don't get the program. The way we talk about this in regression discontinuity world is you have something called a running variable or a forcing variable that determines eligibility. So with SNAP benefits or with Medicaid, that's the poverty line, where you have some level of income, and wherever you fall in that income determines if you get the program based on a cutoff or a cut point or a threshold, and that assigns you access to the program. In DAG terminology, it still works. You can say the program causes some outcome, but being above the cutoff influences whether or not you get the program. And this running variable causes you to either be above the cutoff or not. And often that running variable will also lead to the outcome. So if you're trying to measure health, being poor is going to influence whether or not you get the program, but being poor is also going to influence your outcome there. And so you need to somehow deal with the running variable confounding that. And that's what regression discontinuity lets you do. Okay, so an example of this. We're going to have this hypothetical AIG, this academic and intellectually gifted program that schools do, this gifted program idea. And we're just going to use this as an example to show how this works with regression discontinuity. So in this situation, we're going to say if you score 75 points or higher on some test, you get into this AIG program. If you don't, then you don't. Okay, so let's pretend this test actually happened. And here is a graph of who participated in the program and who did not. And this looks like everybody was pretty compliant with it. People who scored high were in the program. People who scored low were not in the program. In this situation, this is something we call a sharp discontinuity. You don't have anybody who scored high who weren't in the program, and you don't have anybody who scored low that was in the program. Often, though, you'll have something called a fuzzy discontinuity. And this goes to Janelle's question here. If there are limited seats, but policy is first come, first serve, you can still use RDD or regression discontinuity designs, but it will be fuzzy. You will get people who score high who will not be in the program. You might have a situation if people know about the cutoff. Often what happens is if you're like a test administrator and some student got a 74 and you say, you're good enough, I'm friends with your family, and so you can be in the program, then they can suddenly be in the program. And so there can be non-compliance on both of those sides. And so that creates a fuzzy regression discontinuity situation, but you can still analyze it. The whole reason we care about this is the intuition behind this is that basically you have a treatment and a control group. You don't have a treatment and control group here. The people who scored 100 are not comparable to the people who scored like 30. So if you're going to try to say there's our treatment group, there's our control group, that's not going to work very well. The intuition behind regression discontinuity, though, is that the people right around the cutoff are basically the same. And so if you look here, if we limit our analysis to just the people in this light gray range or even the dark gray range, these are people, we can zoom in a little bit more. This person here has scored a 74.9, and this person here has scored a 75.1. They are essentially the same person. It's just that one person had a better breakfast that morning or had a better day or just happened to guess right and the other person guessed wrong. But for all intents and purposes, they're basically the same person. And that is the intuition behind this. And so what you can essentially do is say, here's our treatment group, here's our control group, there's our fake randomized control trial, figure out the difference between those, because they're basically the same people. And that's how regression discontinuity works. That's the basic intuition behind it. So if we look right here, so we have pseudo treatment and control groups. So if we look at this, here's their AIG test score. And then instead of looking at whether or not they were in the program, we're going to look at their final test score that they take at the end of school or whatever. And it's on a scale of up to 100 or something. Again, this is totally fake data. But what we can do is we can see that people who are not in the program, these red dots, they have some trend. where they have, as they increase their AIG test scores, they're going to have higher scores. But then there's a break, and people who were in the program have a different line. They're up higher. That difference right there between the people who scored 74.9 and 75.1, this is the Greek letter delta. It's just the program effect. That right there is the effect of the AIG program on test scores. It increases test scores by like 8 points or 10 points or however big that is there. And that's really cool. You can't have this be totally generalizable to everybody. You can't say universally being in the AIG program boosts your score by 10 points. That's only true for people kind of around this area. If you scored 100 and you weren't in the program, you're probably still going to score high on the final test. If you scored 40 and you were in the program, it'll probably boost you some, but it's not going to be that size. And so the causal inference that you have, you're limited to just kind of this area right here. You have what is called a local average treatment effect. So you can't talk about the whole thing. You're just talking about people kind of around that cutoff there. If we zoom in a little bit more, we can see better. These are the people plus or minus like 3 points around the score, around the threshold there. And so you can see like being in the program boosted their scores. So this is fake data, but people do this stuff with real data all the time. So if you look at this is a really cool paper here that shows, do people, does it being dark at night make it less likely that you will vote? And so the way, like, so basically what they're trying to argue here is, should you have longer voting times, or should you have earlier voting times so that people like can access voting and it doesn't feel like nighttime? And so what they do is they use discontinuities. If you notice here, this is the border for the Eastern to Central time zone. And here's the border for the Central to Mountain time zone, and then a Mountain to Pacific time zone there. And so what they did is they looked at voting precincts just on either side of the border. And so if you are in like Rome, Georgia here, that's pretty close to Alabama, it's going to look different at nighttime or near nighttime at the same time as it is in Alabama because of time zone changes. So what they did is they looked at turnout, voter turnout in both of these districts on either side of that discontinuity. And they found that there's lower turnout in counties on the eastern side of the boundary. So if you are in eastern Alabama, there's going to be lower turnout there than western Georgia because it's an hour later in Georgia. But it feels darker in eastern Alabama. And so there's lower turnout, which is crazy. And so election schedules, depending on like if you have fall time elections, where it's really dark in eastern parts of time zones, that actually lowers voter turnout, which is pretty crazy. And so like that's like a real live regression discontinuity here. People have done this with test scores as well. People have tried to find, is there an effect for going to your flagship state university versus other schools? And so this is trying to measure, like, do you get higher income if you go to the University of Georgia or University of North Carolina instead of GSU or NC State or other places like that? And so the way they were able to estimate this was with regression discontinuity based on SAT scores, where SAT scores are essentially an arbitrary cutoff for getting into UGA or UNC or other places, where if you have a high enough test score, you can get into the university. If you don't, then you don't. So what they did is they looked at this discontinuity here. So there's two different graphs here. So this first one just shows, this is not the effect. This is just showing like if you are below the cutoff for getting admitted to a state school, this is the probability that you get admitted to that state school. So if you're below the cutoff, you only have like a 10% chance of getting into the school. If you're above the cutoff, you have like a 50 to 60% chance of getting into the school. So there's a clear cutoff that's pretty sharp. It's not fuzzy. They're not letting, like, you don't have a high probability if you're 100 points below the cutoff of getting into school. Then what they did is they looked at the earnings of people in those schools around their SAT scores here. So they found that people on average do have higher earnings if they had their SAT scores slightly above the cutoff. And it is statistically significant. It increases your earnings by 9%, basically, is what they found if you go to UGA versus other schools or UNC versus other schools. But it is not wildly significant. And when they do other tests in this paper, they find that that effect kind of goes away. But the intuition is still holds here. It's that same idea as the AIG program. Like this cutoff is determining your access to the program, and then you can use that as basically fake treatment and control groups. And so if you compare these people right around the cutoff here, then that is the causal effect for those people who are right on the border of being accepted or not. Okay, so these things are all over the place. People love them. They're becoming increasingly popular in policy analysis and in economics research, in part because they are compelling. They're highly graphical. It makes more sense intuitively, to me at least, than like difference in difference. It makes way more sense than instrumental variables, which are this bizarre thing of finding causation, which we're not even talking about today because they're weird. There's this cool paper here that shows that regression discontinuity designs are actually less susceptible to p-hacking and other statistical shenanigans than difference in difference or instrumental variables. They're generally more kind of believable and credible. As long as you can find a situation where a cutoff exists in the world and it's a fairly sharp cutoff, you can use that as a treatment and control group and talk about causal inference there, which is really neat. Okay, so briefly, I'll show you how to do this with R. So if you come back to RStudio and open up number 5 here for regression discontinuity, you'll see it either as RD for regression discontinuity or RDD for regression discontinuity design. It's the same thing. So this is, again, that AIG example with fake data that I made up. So if we run that first chunk, we can see here's our AIG program. We have test scores, we have final scores, we have whether or not they are in the program, and some other potential confounders, which we can actually ignore because of how the DAG is drawn. So the first step is we want to determine if getting treatment was based on a rule. And so in this situation, there's no statsy way of doing that. You just have to say, could people access the program because of a rule? And in this situation, because we made it up, yes, they could. If you scored higher than 75 or higher, you're in the program. If you're not, then no. Then to determine, then you have to figure out if the design is fuzzy or sharp. How was the compliance? So to do that, you just plot it. And you say, here's the scores of everybody in the program, everybody not in the program. And it looks like nobody who scored low was in the program. Nobody who scored high was not in the program. So that's a good sharp discontinuity there. If you scroll down to step 3, next we want to see if there's a discontinuity in the running variable around the cutoff. So in the test score. The reason we care about this is you don't want people to manipulate their way in. Like if people know about the score, about the cutoff, then people are going to cluster around 74 and 76 and be really close to it. And once you have that, then the people who are right around the cutoff aren't going to be very comparable. So you want there to be no discontinuity there. And so if we plot it, you can actually see this histogram is fairly curvy. The cutoff is there. There might be a little bit of a jump there, more people getting like 75 or 76 than 74, but it doesn't look huge. If this looked huge, you would see like this red area would be really low, and then suddenly at 75, tons of people are getting 75s. That's a sign that they're probably cheating or there's probably some non-compliance or something. So this is just a way to check that it's fine. If you scroll down, there's official ways of doing it. I have code there for it, but we're going to ignore that. Okay, the last step is we want to check for a discontinuity in the outcome across the running variable. So this is the magic picture here. So the running variable is the test score, and then we want to see if the final score has a jump, and it does. So right here at 75, that's kind of the average test score. And then at 75, it jumps up and it's higher for that group. So there's a discontinuity. Hooray. The last thing we need to do is measure how big that discontinuity is. You could either like eyeball it and say that's like 62 and that's like 71-ish. So that's probably a 9-ish, 10-ish point increase maybe. Or you can actually use regression to do it. Where if you run a regression model here, it explains how to do it here. It's really just a regression model. We're just centering the test score around 75. So it's really just measuring how many points above or below 75 you are. And so what we find is it causes an 8.4 point increase in your final test score being in the program. And that is the causal effect. And then there's a whole bunch of explanation of what all of that means, but that's really all you're doing with regression discontinuity, is checking to see if there's discontinuity and drawing it and then measuring the size of that gap. The important part is there's a whole bunch of different ways of drawing these lines. This is drawing lines with the whole range of data. You can also limit those lines so that you're only drawing the lines like plus or 5, 10, or plus or minus 5 points or plus or minus 10 points, and just limit your data to those people and then draw the lines and then measure the gap. You can draw curvy lines. You can draw straight lines. You can draw whatever lines you want that fit the data the most accurate that you feel. And then in the end, you just measure the gap. And so if you go throughout the rest of this, let's knit it. I actually walked through a whole bunch of different ways of drawing different lines and then measuring the gap using those lines. And I think if you scroll all the way down to the bottom, yeah, here's this table of a whole bunch of different ways of drawing those lines. And you see that the estimate changes. Like 8.4 is what we found just with those two lines, how they were. You can do all sorts of other ways. And so sometimes it's up to 9, sometimes it's as low as 7. So the estimate's kind of all over the map there, but it's not all over the map like negative or 7,000. It's around 7, 8, 9-ish. That's the causal effect of the program. And so you can say, this probably has a positive effect. Let's keep doing this program because it's working. And you can conclude that based on this. And that's really neat. So is it better than using propensity score matching, Mike asks, or any sort of matching or the inverse probability weighting stuff? Sure, it depends on the situation. So again, the inverse probability weighting stuff and the matching stuff, that works with just general observational data that doesn't follow any weird situation. Regression discontinuity follows a weird situation where you have a cutoff and you have people before and after the cutoff. And so when you have a situation like that, you don't need to go to the confound, like blocking all the backdoors. You block the backdoors by dealing with the cutoff. Because as we saw in the DAG, back to here, this is the DAG there. As long as we control for being above the cutoff, that blocks all the backdoors. And so because this is a very specific situational type of design, you don't necessarily need the inverse probability weighting or the matching. Kind of like with diff and diff. If diff and diff exists, you have a pre and a post and a treatment and control, then you can use diff and diff in that situation. Mostly though, when you do this causal inference stuff, you're not going to, like in your day-to-day work, you're not going to necessarily have a fake treatment and a fake control group based around some cutoff. You're just going to have a data set of students or a data set of employees with a whole bunch of different columns. And in that situation, that's where you're going to want to use matching or inverse probability weighting or something else to figure out what things to control for and how to adjust for confounders, because that doesn't fit diff and diff or regression discontinuity. So using this 8-point thing, it is positive, but the owner has to decide if it's big enough. Yep. Yeah, it doesn't tell you if it's huge or not. That's up to you. So if it had like a 2-point increase, maybe it's not worth it. If it had like a 90-point increase, maybe give everybody the AIG program because wow. But it's really just up to you. And that's the case with all of these. So in all of these situations, you're trying to find the causal effect of stuff. So if you do the matching, you get some number. If you do diff and diff, you get some number. If you do an RCT, you get some number. But then you have to decide, is that number big enough for what I care about? Even with this idea of UGA giving you more money, you have to decide if that 9% increase that might not be significant, if that's big enough to care about pushing everybody to UGA, for instance. That's entirely up to you. So that is kind of a super fast crash course into some cool ways of finding causation. Hopefully what you come away with from today is you don't need to be scared of talking about causation. We drill it into your heads in stats classes to never talk about causation. Everything's just correlation. And that is true unless you can tell a good causal story. If you can draw a diag and close all the back doors, if you can have a cool regression discontinuity design, if you can figure out a cool diff and diff situation where you have plausible treatment and control groups, talk about causation. You don't need to be afraid of it, because you can use this stuff to find causation. You don't have to be stuck in the correlation world. So that's what I have. If you have any other questions, ask away. Otherwise, have fun playing with causal stuff.